Hey everyone, so I'm in this video going to walk through the study guide for the final exam, and I'm going to cover both portions, the multiple choice portion, and briefly talk about the SPSS portion. But for the SPSS portion, I'm going to direct you to my other video, but I'll still talk through it a little bit. So yeah, let me start off from the top. I mentioned this in class. The final exam, it's not, it's partially comprehensive, right? These ideas, these topics, they build upon each other, and really, I do think uh, what I want for you is to at least have the basics down very well. So there are a number of questions that just talk about general ideas from previous sections. So this top one right here, I'd definitely spend some time reviewing. You may think you know it, but make sure you know it, because again, there's some questions that just directly tap into these ideas. So, okay, the first off is know how to identify the independent variables and dependent variable in a study. Independent variable is the cause, and dependent variable is the effect. So to let you know what I plan to do in the final exam, I'm going to give you some research questions where I say, oh, I'm interested in if there's a relationship between if you like to sleep in a hard bed versus a soft bed, and the quality of sleep you have. And I would be, and that's just an example, I would ask you what type of variables would you, well, I would ask you what type of statistical test you would need to use to look at that relationship. And so you would have to think about, okay, what type of variables do I have? You would want to be able to identify the independent variable and the dependent variable. So what's the cause and what's the effect? And then based on that, you would want to be able to say, okay, this is the, this is the, it's a t-test because I'm looking at a nominal variable with 2 levels, and I'm looking for the mean, which is the number of hours you sleep per night. So, I'm jumping a little bit. These ideas, it's just knowing how to identify them, but it also is connected to this, because if you these go hand in hand, because if you are trying to identify the type of test you're going to use, you need to be able to do that. Just identify which type of independent variable you have, which type of dependent variable you have, and then put it together and say, okay, oh, that's a chi-squared, or that's a t-test, or that's a one-way ANOVA. All right, now the null versus alternative hypothesis. This is, I would just encourage you to understand the basic idea, which is the null hypothesis is always that there is no relationship between the variables. The alternative hypothesis is that there is a relationship. You know, it looks a little bit different, or you talk about it a little bit differently when you have a t-test versus a regression, but this is the common idea between all of them. So if it's a correlation, you would say the null hypothesis is that the independent variable is not correlated with the dependent variable. All right, so that's an absence of a relationship. If you're talking about a t-test, you're saying, oh, this variable, the group that you belong to, isn't related to this other dependent variable, this continuous variable that we're interested in, and there's no relationship between them. So it doesn't matter what group you're in, it doesn't impact your score on this other variable. This next point, retain versus reject null hypothesis. I think you guys have got this down by now, but again, good to review. So if you have a significant result, reject the null. If it's not significant, you retain the null. Again, when you think about what are these statistical tests, they're always about the null hypothesis. You're always making a decision about the null hypothesis. You're either rejecting or retaining it. And rejecting basically means that your hypothesis that they are related is correct, but it's really essentially about the null hypothesis. If it's not significant, you have to stick with the null hypothesis. This next one, p-values and significance. If p less than 0.05, that means it's significant. Anything else above 0.05 or exactly 0.05, it is not significant. All right, then we have the type 1 versus type 2 error. Type 1 error is a false positive. It's a result that's significant, but in reality, right? So what we observe in our sample is a significant relationship, but reality is there is no relationship there. That's a type 1 error. So anytime you get a significant result, the only type of error you could be making is a type 1 error. Type 2 is just the opposite. You have a not significant result, and it's possible that there is a relationship, and this could be a false negative, that you think there's nothing there, but in reality there is a relationship. Now, I pasted this table in here. It's directly from the slide deck, and I mentioned this. We haven't talked about this first line. The nominal is a chi-square, but I did mention this, that I do want you to know that if you have an independent variable that's nominal and a dependent variable that's nominal, just be able to know that you're going to use a chi-squared. Again, it's not a chi-squared, it's a chi-square, and it's just the type of test that we use in these situations. We don't use it terribly often, but it happens enough that I want you to know what that is. The second type of test was early on. It was our first test. Well, we learned about the three different types of t-tests, but this one in particular is the independent samples t-test. It's where you have a nominal variable with two levels, with two groups, male, female, or I like hard beds or I like soft beds, these groupings that we could belong to. And then the dependent variable would be any kind of continuous variable, number of hours of sleep or quality of sleep. It's got to be continuous. And the question for this one is, are these two groups, are they different from each other on average on this variable here, whatever it is? So that's an independent samples t-test. The one below it is a one-way ANOVA. The only difference between them, you could see it right here, is a one-way ANOVA is done when you have 3 or more levels. So you have 3 or more groups on that independent variable. So it's ethnicity, or if you have placebo, medicine 1, medicine 2, those are 3 different groupings. And the question there is, are these 3 different groups, do they all have the same mean, or is it not all the same? Is it not all equal? And that's a one-way ANOVA. Again, one independent variable, one dependent variable. And of course, that separates it from the factorial ANOVA, which has 2 nominal independent variables. It doesn't matter really how many groups you have. It's really any case where you have 2 nominal independent variables, and you're asking this question, is it related to continuous dependent variable? Then more recently, we've been talking about this, which is the simple regression, a continuous independent variable with a continuous dependent variable. That is a simple regression. If you're only looking for the correlation coefficient, you could also call that a simple correlation. I won't get you confused and ask you, oh, is it a regression or a correlation? Don't worry about that. But yeah, it's just the difference being it's an independent variable that is continuous. Again, you can look up here, it's different from everything else we've learned in the class. And a multiple regression, just know that a multiple regression is when you have two or more continuous independent variables. And you're saying, okay, if I know these variables, if I know how depressed I am and how hopeless I am, can I predict some continuous outcome, like how severe my thoughts of suicide might be? All right, so again, try to get familiar with this. This is the basics of what we've been covering since the first midterm. Let's see here. Then know the situation, and all these are related to this table up above. Know the situations in which to use a one-way ANOVA or a factorial ANOVA. Know when to conduct a simple versus a multiple regression. You know, a multiple regression would be when you have two or more independent variables. Know when to conduct a chi-square test, when it's independent and dependent are both nominal. And know when to conduct an independent samples t-test. So there are a few questions that ask you, okay, here's some variables. So you have to figure out what type of variable it is, and then also figure out which type of statistical test you would use. Okay, then the next set of questions are about factorial ANOVA. So I do present you with, in the multiple choice section, with the factorial ANOVA output, and I ask you to walk me through the findings, the major findings. So you don't have to, you're not actually doing an SPSS in this section, and so you're just trying to explain it and interpret it. So one part is to know how to interpret the numbers preceding a factorial ANOVA. So you've heard this, it's a 2 by 2 or a 3 by 3 or 4 by 5. Okay, what does that mean? So let's say it's a 4 by 5. What that means is because there's this number, the 4, and this number, the 5. Let's ignore that the numbers themselves and just simply say, okay, there's one number, two numbers. Okay. What that means is that there's two independent variables. The number itself is important. So it means that the first independent variable has 4 groups because it's a 4. And the second independent variable has 5 groups because it's a 5. And so this is looking at those two variables, the two independent variables that are nominal. You're looking to see how are they related to some continuous variable. All right, so I might say, oh, this is a 3 by 4. How many variables does it have? How many groups in variable 1? How many groups in variable 2? Okay, so know that the factorial ANOVA allows us to test for an interaction between variables. So this is one of the distinguishing elements of a factorial ANOVA. So it's not just like running a one-way ANOVA for one variable and one-way ANOVA for the other. It's actually bringing them together and looking for, oh, are these two independent variables interacting? Do they impact the relationship of the other with the dependent variable? And so again, just know this conceptually, that's a purpose, one of the purposes of the factorial ANOVA. Of course, the other purpose is just to make it easier on us, to make it so we have less tests to run. So that's one purpose. But the second is to look at them together and look at, when you combine them, is there anything unusual in the combination of the variables? The one-way ANOVA can only test for the main effect because there's only one variable in it. So you can't test an interaction when you only have one variable. And so that's what the factorial ANOVA can do. And then finally, know what interaction is conceptually. And I've kind of explained this already. It means when one variable, the effect of one variable depends on another variable. the way that one variable relates to the dependent variable depends on another variable. So if you are, let's give an example. If you take a medication for depression, the effect on depression might be different depending on if you're male or if you're female. So you cannot just look at the medication or the placebo. You have to look at the medication and the gender at the same time, because only then do you understand how it might relate to the dependent variable. All right, and the assumptions of the factorial ANOVA, we did walk through these, so do be familiar with them. These first two I think we've got down pretty well: random sampling and scale of measurement, just making sure it's the right type of variables, which is basically going back up to here and saying, okay, it's got two nominals that are both, two independent variables that are both nominal, and a dependent variable that's continuous. So that's what this one is all about. The normality of the dependent variable just means whatever you're trying to predict, is it normally distributed? So that's the question there. And then finally, quality of variance. And we only check that if the interaction is not significant. So keep that in mind, that you don't worry about the quality of variance if you have a significant interaction. It's only if the interaction is not significant. Okay, and then let's see here, other ideas. These are about the regression. So here is the null hypothesis of the intercept. I can just add in here, I'll type it in. It is that the intercept equals 0. Okay, and the null hypothesis of the slope is that the slope equals 0. Just keep in mind again that the null hypothesis is always nothing, right? It's a 0. So this kind of makes sense that the intercept, we start off thinking, oh, it just goes right through that y-axis at 0. That when x is 0, y is 0. So you have to test and see, oh, was it different? This is not the most important one. This is not really all that interesting to us, because oftentimes it's not 0, even if there's no relationship between the variables. So that doesn't matter all that much. The slope is a lot more interesting and a lot more informative. So when you talk about is there a slope, it's slightly different, but it's related to this idea of, is there a correlation between the x and the y variable? So the slope, if it's positive, it means that as x goes up, y goes up. It means that there's a positive correlation, if it's significant. And if it's negative, it means there's a negative correlation. So the numbers are different. The number for the slope is not the same as the number for the correlation, but the idea still applies. Okay, and again, the initial idea is there's no relationship, that regardless of what you are in x, your y is always the same. That's the null hypothesis. Only when you can reject the null hypothesis, say, oh, the actual prediction of this is is better if I take into account the x. Then we have how to interpret an r squared. So I might give you, oh, r squared equals 0.244. How do you interpret that? Well, the answer would be 24.4% of the variance in the y variable, in the dependent variable, is explained by the x variable, the predictor variable. So SPSS gives you an r squared, it's a number. And all you have to do is if it's 0.244, you take that decimal point, move it over 2 places. So instead of 0.244, you move it to the right 2, and it's now 24.4, and it's 24.4%. And the percent is how much of the variance in y that it explains. If you're talking about just one x and one y, the r squared is just literally the square of r, the correlation between the two variables. That's all it is. So if you know your math, you know, and well, I'll actually pull out the calculator here so you can see it. Let's say if you have a correlation of 0.4, and you square it, you get 0.16. So that means that if your correlation is 0.4, then 16% of the variance in y is explained by x. And if the correlation was 0.6, if it's a strong correlation, that means 36% of the variance in y is explained by x. Now for this next one, it's really plug and play. Basically, if I say y equals 6 plus 4x, and I give you x, I might ask you to find y. So if I say x equals 4, you just plug that in here. So 4 times 4, 16, plus 6 is 22. So y is 22 if x equals 4. And let me show you real quick a regression table, if I can. And this is our data set from the final exam. So if you look at this, if you run a regression, a linear regression between, let's look at whether money buys happiness. Okay, I forget if this is significant or not. All right, so if I go to the output, it is not significant, 0.32. So there, in this case, it's fake data, but we didn't find a relationship between income or money and happiness. So what did we find? Well, this B is a little unusual because it's got an E in it. So if you know scientific notation for numbers, you know that means it's a very, very small number. So here you could see it. So you can construct an equation, and it's, I'll type it on the screen. So happiness equals 5.585 plus, and it's very, very small, 4, yes, 4 zeros and then 11 times, I'll make it a little bit larger here, times income. So if my income is, let's say, 100,000, just because that'll make it easy. Perhaps it'll make it easy. Oh. And I guess for my math isn't that great, so I'm going to do it with my calculator. 100,000 times 0.000011 would be 1.1. So if my happiness is, if my income is 100,000, my happiness is 1.1 plus 5.8 or 5.585, 6.685. All right. Now, if it was 50,000, well, I could take 1.1 divided by, so, well, let me show you how this might work, is 50,000 times 0.000011 5.585. So my happiness would be predicted to be, if I'm making 50,000, it would be predicted to be a 6.135. I don't know what the scale is, but maybe let's say it's out of 10. So I'm a 6.14 if I have an income of 50,000. And if you recall, my happiness would be a 6.68 if I had a income of 100,000. So that's a big gap, 50,000 to 100,000, and it doesn't actually correlate much with happiness. So it's 6.14 if I have an income of 50,000, 6.68 if I have an income of 100,000. So not a huge difference. Basically, we conclude that there's not a significant relationship there, that as income increases, there's no change in our ability to predict what our happiness will be. So it's, yeah, there's a slight difference there, but it's not big enough to say it's a significant relationship. So just know how to work with this. You're looking at the b and you're plugging in the b, the constant here, and then the b for the x variable here, and then just multiplying it by some value. And so just know how to do that. Know how to interpret an SPSS table for regression. Okay, and then the SPSS portion, I'm going to just, again, direct you to one of my other videos on factorial ANOVA. I posted that on YouTube. So that walks you through how to conduct it in SPSS, how to test the assumptions, how to report the findings with APA style. And then you'll just need to know how to upload on Canvas, which I think you know by now with the test, is just to click the upload button. So there's not a simple regression, so you don't have to do that. I'll scratch that out, so you don't have to do that. But yeah, so I think you'll be able to do the SPSS portion without much trouble. So let me just briefly talk about the short answer. If you go to my slide deck on factorial ANOVA, you'll find there's a slide here at the beginning where I talk about scientific humility. And I point out that in science, and I've talked about this throughout the class, it's a very odd stance that science takes. It says we have ideas, but then we actually assume that they're wrong. We assume that they don't apply to the situation until the data proves, or not proves, but shows that there's a relationship there. So I think this is an example of scientific humility, that built into the approach is this idea that we come up with new ideas, but we hold them loosely. You doubt your own ideas until the data support them. I've had some students write this on their final exam, be a humble genius. It's actually meant as a joke. You know, I don't think it's helpful to call yourself a genius, even if you are. But just this idea that even if you are a genius, you don't have to, you actually shouldn't assume you're right, because even geniuses are wrong quite a lot when they're thinking about new ideas. So it doesn't matter. It's not a sign that you're not smart if you come up with an idea and it doesn't prove to be true. That's just not how it works. You never know how a result will turn out. And you may come up with a very brilliant and insightful hypothesis, but it might not actually match up with reality. And so that's that scientific humility to say, you know, regardless of how smart I am, I'm never going to quite get this right, or never going to be entirely accurate all the time, at least. I'll get it right some of the time, but maybe not all the time. So that humility is so crucial, and I think we live in a world where, you know, corporate executives and tech industry, they come up with these ideas and they don't have this scientific mindset of saying, all right, well, that's a great idea, let's test it and make sure that it works. Some corporate executives, some tech industry people do this. In fact, if they do it, they probably do better in their work. But then there are others who just assume that they're going to get it right all the time, and I think that's being full of yourself and being prideful. So that's what I mean when I mean scientific humility, and hopefully that's come throughout this whole course, so you can expand on this idea. I want you to put it into your own words about, you know, we're starting off with the null hypothesis, and explain it from that idea. And so you can talk about this. Despite the fact that we came up with the idea, we assume there's no pattern unless the data is inconsistent with this assumption. All right, so that is for this one, concept of humility, but also discuss the limits of science. And well, if you're watching this for my spring 2020 class, I just talked about this today. In our final lecture, I had this slide here that talked about the importance and goodness of science, but also you can say that science is good and also say that it has some real limits. And so you need to understand that the science is prescriptive. It's not, science is not prescriptive. It is descriptive. It tells us how things are. So science is descriptive, not prescriptive. It doesn't say how things should be or how we should act. It doesn't say much about ethics. It just says this is the way things are. And so as a result, we can take that and we could recognize that science is good. Science will provide us with truth about some things, but not about everything. That there are some things that we need to turn to other ways, not scientific ways, to know. And I always give the example of history. You cannot prove history with science. You cannot prove scientifically that Abraham Lincoln lived. So you have to learn about history with other methods, you know, reading historical sources and things like that. And so that's really what I want for you. I want you as students to appreciate science and what it can offer, but also recognize it's not going to solve all of our problems. And there's some things that, especially issues of faith, where we turn to other ideas. Another way to think about it is from an early lecture. And let me see if I can find it here. The distinction between nomothetic and idiographic. Nomothetic is that which is general, common, and replicable. Science can discover truth about the nomothetic. The idiographic, though, is that which is specific, unique, and historically distinct. It cannot tell us about the idiographic. It cannot tell us about personal experience, intuition, and faith. And so you might want to bring this in, this distinction between nomothetic and idiographic when you're talking about the limits of science, because science relies on replication. If you're talking about idiographic, you're by definition talking about things that aren't replicating. These are things that are unique, and so science cannot answer it. All right, well, hopefully this will be helpful to you all as you're studying. Hopefully this test is not too intimidating or anxiety producing. I think you will do just well as you take it. So do prepare for it though. Study well, and I wish you the best. And so take care, have a great summer, and we'll be in touch. Okay, bye.